In this video tutorial, we're going to demonstrate how to model net metering version 2.0 projects using the newest release of the Energy Toolbase platform. Here is our agenda for this video tutorial. I've attempted to organize these topics in a logical order so that they're building on top of each other. And as you can see, I have the start times listed for each topic if you want to jump ahead to a section. I'm going to start this video reviewing some terminology, so we're all on the same page as I'm using these terms throughout the video. So NEM 1.0, or traditional net metering, assumes full retail value compensation on energy being backfed to the grid. Therefore, NEM 2.0 is a scenario that assumes exported energy is getting valued at less than the retail rate of energy. In other words, a kilowatt hour exported is worth less than a kilowatt hour imported. Imports is simply energy measured in kilowatt hours being consumed from the grid, and exports is energy being backfed to the grid, generally by a solar system. The retail rate is the dollar per kilowatt hour volumetric rate a customer pays on that imported energy, and then the export rate is simply the dollar per kilowatt hour volumetric rate a customer is getting credited at when exporting energy. And lastly, non-bypassable charges, which we're going to cover pretty extensively later in the video, are dollar per kilowatt hour volumetric utility charges that cannot be offset by solar exports. Setting up NEM 2.0 projects. So as you can see, I'm in step 2 utility rates of the edit proposal screen, and down on the bottom of the screen under the new utility rates section, we have the opportunity to define the net metering type. So I'm going to click into this hyperlink, which is going to bring up a pop-up window, and here's where we do all the setup and configuration of our NEM 2.0 scenarios. So let's start at the top under the metering type. And as you can see, the default is full retail value net metering. And as we just talked about in the terminology section, this is simply assuming that all exported energy is getting valued at the full volumetric rate based on whatever rate schedule you define in step 2. Let's talk about this scenario next, which is no net metering fixed rate on exported energy. So I like referring to this as the either Hawaii scenario or the Nevada scenario, because that's how both of those successor tariff frameworks were set up. And effectively what this means is, if and when a system is exporting energy back to the grid, that energy is getting valued at X. However, the user defines X. In this case, it's at a nickel. So that's pretty straightforward. Let's talk about the other scenario, which is the retail rate net metering with non-bypassable charges scenario. And I like referring to this one as the California scenario. So effectively what this means is this. The user is going to come down here to the bottom of the page and is going to define what that non-bypassable charge rate is. And this is effectively saying, let's hypothetically assume that the retail rate of energy is 20 cents a kilowatt hour. And if the users define the non-bypassable charge rate at 2.5 cents a kilowatt hour, that effectively means that all exported energy is going to get valued at 17.5 cents a kilowatt hour. We're basically just discounting off of the retail rate on exports. Okay, now let's talk about the net metering true-up period, which dictates the time frame over which NEM credits are settled. So you can see here the default is an annual true-up period, which is basically establishing a 12-month true-up cycle for those NEM credits. So for example, if a customer finished the month with a credit balance of NEM credits, those credits can be carried forward and are all going to get trued up over 1 year. Whereas in a monthly scenario, let's say a customer finished the month as a net exporter of 100 kilowatt hours, those 100 kilowatt hours are going to get settled at the end of each billing period, and they're going to get valued however we define the compensation at the end of the true-up period, which we're going to talk about next. Okay, and lastly, let's talk about the compensation at the end of the true-up period, which determines how to value net exports at the end of their true-up period. So the best way to think through this is with an example. Let's assume a customer was a net exporter of 100 kilowatt hours at the end of their true-up period. And as we defined it here, we're saying their true-up period is monthly. This is basically saying, choosing this option, those 100 kilowatt hours of net exports are going to get valued at the wholesale rate of X, however we define X, which is a nickel in this case. Whereas this option here is basically saying those 100 kilowatt hours of net exports at the end of their monthly true-up period are going to get valued at 0. So that should be pretty straightforward. One other very quick point that I want to make, a lot of times the wholesale energy rate is referred to as the net surplus compensation rate. And again, the net surplus compensation rate is simply determining the value of exported kilowatt hours at the end of their true-up period. Determining exports. So to accurately calculate the avoided cost or value of solar in a NEM 2.0 scenario project requires that we realistically estimate how much energy is getting exported back to the grid. And it's important to note right up front that for Energy Toolbase, or any software program in the world for that matter, to realistically estimate exported energy requires that the user starts with interval meter data. So here I am on our Create Energy Use Profile screen that most of you are familiar with. And as you know, 5 of these options are working with interval meter data. And for those of you that are less familiar with this, just to kind of run through a couple examples of this, here's an example of a interval meter data file in a multi-column Excel format. Here's an example of a interval meter data file in a single column Excel format. Here's an example of a data file in an XML file format. And different utilities in different parts of the country output to different file formats. And it's really cool with an Energy Toolbase. We've engineered this so that we can import raw meter data from any of those file formats right into the tool. I also want to make very quick mention of our friends over at Utility API, who we just completed an integration with. So if you're using the Utility API service for fetching your interval data files, you can now import those directly into Energy Toolbase. Okay, so here I am on the Edit Lead screen, and you'll notice I've created a facility called the Residential House Meter. And underneath this facility, I've brought in 2 separate interval meter data files. And I've named one of them the Night Owl and the other the Midday Peaker. And I've done this to illustrate a point. Both of these data files are real usage from real homeowners in Southern California. And what's going to help make this point is that both of these just coincidentally happen to use approximately 12,000 kilowatt hours annually for usage. All right, let's jump into one of these proposals and give some context for what I've got set up here. So let's go right to step 2, utility rates, and see the fact that I'm referencing, to start with, the Midday Peaker energy use profile. And over here in step 4, let's just get some context for the solar system I've designed. It looks like a pretty straightforward 6 kW system facing 180 south, 18-degree tilt, and this is in San Diego. So now I'm going to come down to the facility summary, and here's where we can really see a great summary of the project, and we've already actually solved for how much energy this particular scenario is exporting back to the grid. So as you can see here, this is a 6 kW system. The customer is using about 12,000 kilowatt hours. The system is producing about 9,800 kilowatt hours, which translates to about an 81% offset in terms of kilowatt hours annually. And then over here on the right, this is a really great number to be able to reference. We've already solved for how much of that kilowatt hours is being exported back to the grid. In this case, 31% of the 9,800 are exported back. Okay, now let's look at the back end and unpack how we're getting to that 31% export value. So I'm going to go into ETB Analytics. I'm going to go right to the demand profile visualization screen. So I think the best way to look at this is to remove the production side first and just kind of zoom in, how about on a week of just usage data. And what I like to do is just hover my mouse over the peaks. So as you can see there on bottom, on January 27th, this particular load customer was peaking right around 11:45 or noon. Here we are a day later on the 28th, 12:45. 25th, 12:15. Let's go down to a summer month. I actually always think it's good to just look at both a winter and a summer month to make sure we're thinking about seasonality. Let's go into about a week here. And again, as I hover my mouse, we're really seeing kind of a midday load profile, which is why I descriptively named this customer the Midday Peaker. Okay, so now let's think about exports. So now let's overlay our solar production data based on that 6 kW 180 south facing system that we ran in PV watts. And let's also overlay net. And now we can visually see on the chart all of the energy below the line, which effectively represents exports. Okay, I also want to quickly show users how to download out data if that's what they prefer to do. So also in the ETB Analytics tab, under the Download Proposal Data screen, let's take out the net usage file. And we actually looked at this in a previous video, but I want to actually show you how to manually calculate exported energy if that's how you prefer to do it. So this is just one way. I'm going to actually create a separate tab. I'm going to copy paste everything from this first tab into this second tab. And now I'm going to write a formula that says if, referencing back to the original tab, this value is less than 0, then give me that value. And if it's not, give me 0. So if I wrote that correctly, basically it's going to only show the negatives. So I'm going to copy that all the way down. I'm going to snap this across to the entire data file. And now as we scroll over through this data set, we should see some negatives. There they are, which basically represents all of the exported energy or intervals where more energy is being produced and backfed to the grid than it is being consumed. And if you want to actually just sum up this value, it's actually really simple. We could just say sum of this entire file. And don't forget, the last thing we have to do is just divide it by 4 because these values are all in kilowatt unit of measurements, whereas we want to look at this value in a kilowatt hour value. So there it is there, 3,083. And that's the exact same number, if you think about it, referencing back to the fact that we produced 9,800 kilowatt hours, of which 31%, or 3,083, are being exported back to the grid. Okay, now I want to illustrate a point about exported energy. So we're back in this original proposal. I'm actually going to navigate back to step 2, utility rates. And remember, this is all referencing that midday peaker profile. And the fact that 31% of all 9,800 kilowatt hours is getting exported back is really primarily a function of that unique customer's load profile. So let's now toggle this down to the night owl profile. And before I do that, remember this. The midday peaker uses about 12,000 kilowatt hours of usage. Okay, so now let's go to the night owl and let's save this. And this should update real time on my bottom ribbon there. And check it out. The usage really hasn't changed much. This user uses approximately 12,000 kilowatt hours. We're still offsetting about 81, 82% of their kilowatt hour on an annual basis. But look at exports. That number effectively just doubled, which really seems incredible, but this is real, true math. And again, really illustrates the point I'm making. So let's go into the back end again and look at what just happened. Into the ETB Analytics, let's go to the Demand Profile Visualization screen. And here we are in the summer. Let's remove some of these variables and actually just zoom in on a series of days. And as I hover my mouse over the screen now, look at when this customer is peaking. And just look at the shape of their load profile. From 7:45 to 1, 2 a.m. is when this customer is really using the bulk of their energy. Here they are a little bit earlier in the day, 6:30 p.m. to 2 a.m. Here they are on July 24th, 8:45 p.m. Let's just go down to another month just to kind of eyeball that. But again, just zooming in on any random series of days, you can really see that later peak, right? So this customer is peaking much, much later at night, 9, 10 p.m., in some cases even after midnight. So now, as we overlay solar and also net, what happens is a lot of times you'll just see so much more exported energy because their load profile is completely opposite, really, of their solar production file. So to wrap up this section, the point that I was really trying to illustrate is that you can have widely varying degrees of exported energy for customers that have the exact same amount of usage over a year in this case. Calculating the avoided cost of an NEM 2.0 project. Okay, quick recap. So we've talked about how to set up our NEM 2.0 scenarios, and I've explained how we determine exported energy. Now we're going to discuss how these two tie together, which allows us to calculate the avoided cost, or how much a project actually saves in dollar terms. So to demo this, I'm going to run through a couple real-world examples, and these are really going to illustrate how avoided cost will change as a result of the NEM 2.0 assumptions that we define. So I'm going to start with a Hawaii residential project, which is a really easy example to set up and also makes sense of the results. So I'm going to jump into this proposal I had just set up, and let me just kind of start by giving you a little bit of context for what I've got here. So going to step 2, you'll notice I've got that same energy use profile, the night owl, which is, again, it's just a residential customer who happens to peak late at night. And now I'm just going to go to the bottom and dock the facilities dashboard so we can really just kind of talk through a summary of what we set up so far. So as you can see here, we've got a 6 kW DC rated system producing 8,578 kilowatt hours annually. And just as a disclaimer, I use the PV Watts version 5 API with a Hawaii weather station to come up with that number. And we can see here, this offsets 71% of the annual kilowatt hour consumption for this customer. And we can also reference the export amount over on the right. 59% of that production, 59% of that 8,578 is being exported back to the grid. Okay, so now I really want to focus your attention on the avoided cost value, or as we're titling it here, blended savings, which we're expressing in dollars per kilowatt hour. And just to kind of take a step back, the formula on this is really simple. This is simply first year total dollar savings divided by first year total kilowatt hour production. So as we can see here, for this customer, based on the assumptions that we've set up, the total avoided cost or blended savings is 25.4 cents per kilowatt hour. Okay, now we're going to unpack things a little bit more in step 2. Let's start by looking at the rate schedule they're on, which is the Hawaii Electric Company Rate Schedule R, which is a residential schedule, both for current and new. Now under the new, I want to reference which net metering type we're using. So clicking into this pop-up window, we can see that we're now assuming full retail value net metering. So the 25.4 cents of avoided cost or blended savings was under the full retail value NEM assumption. The question then becomes, what happens when we switch this to a net metering version 2.0 scenario? And a little bit of really quick background information on this. In Hawaii, there are a couple of different types of net metering version 2.0 frameworks. One of the frameworks is called the Customer Grid Supply Option, which basically values all exported energy at a fixed rate based on which island the customer is on. So on Oahu, which is where I set up this project, the Customer Grid Supply Option export rate is 15 cents a kilowatt hour. So now that I've set that up, I'm going to save the project back in the proposal editor screen, and our dashboard on bottom is going to update real time. And the really key value that we're all looking for now is what it just did to the blended savings. If you notice, it just went all the way down to 19.4 cents a kilowatt hour from 25.4 cents earlier. So a full 6 cent per kilowatt hour drop or reduction in savings. Also, you may be referencing down on the transaction summary side what that just did to the payback period or rate of return or any other financial metrics that you set up in that transaction. All right, so once you've gotten your head around that workflow, you'll realize how easy it is to calculate the avoided cost of any type of NEM 2.0 scenario. So let's jump in and test out a really extreme case together. I'm going to go back into the metering type, and I'm going to actually set exports at 0. And you're probably thinking to yourself, that's a completely unrealistic assumption. But ironically, in Hawaii, there's actually a NEM 2.0 program called the Customer Self-Supply Option that does exactly that. Now, granted, we're not going to be sizing a system that exports back 60% of the production to the grid without a battery system on there on the Customer Self-Supply Option. But nevertheless, this will be a good illustration of kind of what I want to show here. Okay, before I press save, let's really quickly reference the value of solar, 19.4 cents, and the payback period down on the bottom right, 9.2 years. Any guesses what's going to happen when I save here? There it goes, updating real time. Value of solar collapsing all the way down to 10.6 cents, and the payback period going all the way out to 15.7 years. So a real kind of extreme illustration of when you value exports at 0 and just discount them completely, what that'll do to avoided cost and also the project economics. Optimize the solar system size of an NEM 2.0 project. Okay, I now want to demo how to use the ETB optimizer in conjunction with everything we just looked at. So I'm in this same proposal and I'm in step 4, and I'm going to click into this array, and in the bottom right is the ETB optimizer button. So we're going to run one of these, which is going to run our simulations and give us 6 separate charts. So I want to go right down to the bottom right chart to begin with, which is the annual PV exported generation chart. And if you look at the legend, in blue we're showing the exported energy, in green we're showing the percent of production being exported out. So as I hover my mouse on this chart for a 3.4 kW system, we can see exactly the values both in kilowatt hours and on a percentage basis. And as I just kind of move up the chain here, we can see exactly how the curve and these values are changing as we're sizing a bigger system, in this case a 6.7 kW system. Okay, now I want to go to the top left chart, which is the blended electric bill savings. This is what we've been talking about the whole time, the avoided cost. And I'm actually going to remove this line here because I just want to show the after, which is where we've set up those NEM 2.0 assumptions. So again, the x-axis is the kW DC rating, and the y-axis now is the kWh avoided cost rather. So as I start scrolling down the chart, you can actually see how dramatically that value is falling off. Now, as a disclaimer, I actually didn't change any of the assumptions, so this still assumes that exported energy is being valued at 0, which is why we're getting this really steep effect of declining avoided cost. So last point on this, keep in mind the different data values that we're referencing when we're simulating these charts. So number one, of course, we're using the unique load profile that you brought in. In this case, this is all based off of that night owl energy use profile. We're also, of course, referencing the rate schedules that you set up in step 2, both current and new. And then lastly, we're also referencing the solar production data that you've chosen to use. So scrolling up here and referencing back, this was all based on PV Watts version 5, an 18-degree tilt, 170 southeast, 6 kW DC rated system, and you can see all the PV Watts V5 system loss variables. So if your choice was to work with an outside production tool like a helioscope or a PV Complete, we're going to generate all of these values off of your preferred production tool. So I think it really illustrates the power and sophistication of Energy Toolbase for these sorts of applications when you're using the ETB optimizer on a NEM 2.0 project. That concludes our video on how to model NEM 2.0 projects. Hopefully that gives you the guidance you need to analyze and optimize any sort of use cases you're dealing with. If you are a current customer of Energy Toolbase, feel free to get in contact with us if you have any questions or comments. We'd like to hear from you. Thanks.